Download this code from codegive.com, link in the description below. OK, here's a comprehensive tutorial on Openacc for Fortran programmers, inspired by Michael Wolfe's approach and covering essential concepts with code examples. This guide focuses on practical application and understanding how to leverage Openacc to accelerate your Fortran codes. Openacc for Fortran, a deep dive. Introduction. Openacc, Open Accelerators, is a directive-based programming standard for parallelizing applications on heterogeneous systems, particularly those with GPUs and other accelerators. It provides a relatively simple way to offload computationally intensive regions of your code to the accelerator without requiring extensive low-level programming like cuda or opencl. This tutorial will guide you through the fundamentals of Openacc with a focus on Fortran code. Why Openacc? Ease of use. Directives allow you to parallelize code with minimal changes to your existing Fortran code. Portability. Openacc is supported by multiple compilers, NVIDIA, Cray, PGI/NVIDIA, etc., offering a path to portable code. Performance. Significant speedups can be achieved by offloading computationally intensive kernels to accelerators. Incrementality. You can parallelize your code incrementally, starting with the most time-consuming sections. Key concepts. 1. Directives. Openacc uses directives to guide the compiler on how to parallelize and offload code. Directives are compiler pragmas that start with $acc or $omp, openmp, but will focus on Openacc. The compiler may ignore the directive if Openacc is not enabled. 2. Regions. Openacc directives typically define regions of code that are targeted for parallel execution or data management. 3. Data management. Crucial for performance. You need to tell the compiler how to transfer data between the host, CPU, and the device, GPU or accelerator. Copy, allocates memory on the device, copies data from the host, and copies data back to the host after the region. Copy-in, allocates memory on the device and copies data from the host only. Copy-out, allocates memory on the device and copies data back to the host only. Present, assumes that the data is already allocated on the device, often used when data resides in a previously offloaded region. This can be a potent optimization if used properly. Create, allocates memory on the device without copying data. Useful for variables initialized on the device. Device specifies that a pointer is already pointing to device memory. Attach, attaches an already allocated device side memory region to a host side pointer. Host specifies that a pointer is pointing to host memory even within a device region. Private, creates a private copy of a variable for each thread or gang, within a parallel region. First private, like private, but initializes the private copy with the value from the host. Default, none, forces you to explicitly specify the data attributes for all variables within the region. This is highly recommended for correctness and performance. 4. Parallel constructs. Parallel, creates a parallel region where the code is executed by multiple threads. The work is divided among the threads. Loop, specifies how to parallelize a loop within a parallel region. This is often combined with parallel. Kernels, instructs the compiler to automatically identify and parallelize regions of code within the marked region. It's a higher level approach compared to parallel loop. Update, forces the explicit transfer of data between host and device. 5. Asynchronous execution ** Openacc allows you to overlap data transfers and kernel execution using async. This can improve performance by hiding the latency of data transfers. 6. Gangs, workers, and vector length ** These parameters allow fine-grained control over parallelism. Gang, a group of workers. Think of this as a block in CUDA terminology. Worker, executes within a gang. Think of this as a thread within a block. Vector, the number of vector lanes within a worker. Vectorization is the execution of the same operation on multiple data elements simultaneously. A simple example, vector addition. Let's start with a basic example, vector addition. We'll parallelize the addition of two arrays. Explanation $*. $ACC data copy in, A, B, copy out, C. This directive defines a data region. It allocates memory for A, B, and C on the device. Copy in, A, B, copies data from the host to the device, and copy out, C, copies the result back to the host after the computation. $ACC parallel loop, this directive tells the compiler to parallelize the loop. The compiler will automatically divide the work among the available threads on the device. $ACC end data, this marks the end of the data region. It ensures that the memory allocated on the device is deallocated, and data copied back, if necessary. Compilation *. To compile this code, you'll need an Openacc-enabled compiler. For example, using the NVIDIA HPC SDK. ACC enables Openacc, and minfo = ACC tells the compiler to provide information about which parts of the code were successfully parallelized. A more complex example, matrix multiplication. Now, let's tackle matrix multiplication, a more computationally intensive problem. We'll use a tiled approach for better performance. Explanation **. Tiling ** The code is tiled to improve data locality and reduce memory access overhead. We process the matrices in blocks, tiles, of size tile_size x tile_size. This is a common optimization technique for matrix multiplication on GPUs. Collapse, 2. This clause tells the compiler to collapse the two inner loops, I and j, into a single, larger loop, allowing for more efficient parallelization. Loop gang worker vector, this clause allows you to specify the parallelization strategy. Gang divides the work into groups, worker assigns work within each gang, and vector uses vectorization, SIMD, within each worker. You can adjust these parameters to optimize performance for your specific hardware. Important considerations **. Data locality ** Optimize your code to maximize data locality. Tiling, as demonstrated in the matrix multiplication example, can significantly improve performance by reducing the number of accesses to global memory, which is slow. Data transfer overhead * Minimize the amount of data transferred between the host and the device. Use present to avoid unnecessary data transfers when data is already on the device. Consider using asynchronous data transfers, async, to overlap computation and communication. Compiler optimization * The compiler plays a crucial role in Openacc performance. Experiment with different compiler flags and directives to find the optimal configuration for your code. Pay attention to the compiler's output, example using minfo = ACC, to understand how the code is being parallelized. Data dependencies * Be aware of data dependencies. Openacc relies on the compiler to automatically identify and resolve dependencies. However, in some cases, you may need to use reduction clauses or other techniques to handle dependencies explicitly. Error handling. Enable error checking in your Openacc programs. The environment variable acc_debug equals 1 will display runtime information about Openacc execution. Also, use the acc_get_state and acc_get_device_number routines for status information. Advanced topics. Asynchronous data transfers and computation. Async 1 assigns an asynchronous stream ID of 1 to the data transfer and the parallel loop. This allows the transfer and computation to occur concurrently. Wait 1 ensures that the data transfer associated with stream ID 1 is completed before the parallel loop begins. Update device B async 1 start async copy to device. Update host C async 2 start async copy to host. Reduction clauses used when a loop accumulates a value into a shared variable. Reduction plus sum specifies that the sum variable is being reduced using the addition operation. Openacc will create private copies of sum for each thread, and then combine them at the end of the loop. Kernels construct a higher level approach where the compiler attempts to automatically parallelize the code within the region. Device selection. You can control which device is used for Openacc execution using the acc_device_number environment variable. Deep copying. For complex data structures like derived types containing pointers, you may need to implement deep copying to ensure that the data is correctly transferred to the device. Common pitfalls. Incorrect data management. Forgetting to transfer data to the device or not copying results back can lead to incorrect results or runtime errors. Use default, none, liberally. Data races. Parallel regions with unsynchronized access to shared data can lead to data races. Use reduction clauses or other synchronization mechanisms to avoid data races. Performance bottlenecks. Poor data locality, excessive data transfers, and inefficient parallelization strategies can limit performance. Profile your code to identify bottlenecks and optimize accordingly. Debugging tips. Compiler output. Pay close attention to the compiler's output, especially when using the minfo equals acc flag. The compiler will provide information about which parts of the code were successfully parallelized and any potential issues. acc_debug environment variable. Set the acc_debug environment variable to 1 to enable runtime debugging information. This can help you identify errors related to data transfers, device execution, and other Openacc related issues. Profiling tools. Use profiling tools to identify performance bottlenecks in your code. NVIDIA Nsight Systems and Nsight Compute are powerful profiling tools for GPU-accelerated applications. Smaller problem sizes. Debug your code with smaller problem sizes to make it easier to identify errors. Conclusion. Openacc provides a powerful and relatively easy-to-use approach to accelerating Fortran applications on heterogeneous systems. By understanding the key concepts of data management, parallel constructs, and asynchronous execution, you can effectively leverage Openacc to achieve significant performance improvements in your codes. Remember to profile your code, experiment with different optimization strategies, and carefully manage data transfers to maximize performance. With practice and attention to detail, you can harness the power of Openacc to solve complex scientific and engineering problems. Good luck! Remember that best practices evolve with compiler technology, so always revisit your parallelization strategy as new compiler versions are released.